Welcome to Education with Eleanor. Hi, I'm Eleanor, that's me. And click the subscribe button and hit the notification bell to get more videos on physics, mathematics and science. Hit the thumbs up so that you can like the video if you do. So remember, physics is a beautiful story and it's of how the world works. In this video, we are going to learn about how fast we can actually drive through a roundabout without skidding off, and it's going to be on a banked surface, an angled surface. This is important because if we go too fast, we're going to skid off or shoot off the roundabout, and that's really unsafe because we might have a crash, or most likely we'll have a crash. But if we go at the design speed or slower than the design speed, we can navigate the turn slowly. In physics, this is known as banked circular motion, or a centripetal motion problem, a banked centripetal motion problem. The main idea of this is to find the maximum design speed at which a car can drive through a turn without skidding off. In order to do so, we are going to balance the vertical forces and then the horizontal forces, and along the way we are going to resolve the vectors of the friction force going down the slope as well as the normal force that is coming reacting off the slope. When we resolve the forces, we will get the component horizontal force and the component vertical forces, so that we can get the vertical force balance and the horizontal force balance. So let's get into the meat of the video. Okay, we have banked circular motion, and this is with friction. We're going to calculate the maximum speed that a car can be driven around a bend without skidding off a road. This road is banked at an angle of 15 degrees. So we've got this car traveling around. It's a 1,300 kilogram car, or 1,300 kilograms. The radius is 13.0 meters. The total sideways friction is 15,500 newtons, and it's acting on the wheels. I've put some information here about the vertical forces and the horizontal forces. Remember that the net force for centripetal motion is always the mass times the velocity squared, or speed squared, divided by the radius. So let's just first draw our diagram and go from there. But before we even do that, we need to also write down that theta, our angle, is 15 degrees, and then our mass of the car is 1,300 kilograms. And then we've got a radius of 13.0 meters. And our friction, so I'm making a capital F with a subscript F, is 15,500 newtons. We're going to assume it's towards the center of motion. The reason being is the car is not skidding off the road. The car is going into the bend. So what we need to remember is, when we have banked motion, okay, and the car is going around, if the car is going too fast, okay, then the force of the car coming in is going to exceed friction and the centripetal forces, and it'll go out. So if it's too fast, it won't go around the bend. But if it's at the maximum design speed, or if it's slower, then it'll go around the bend. You'll turn into the bend. Okay, so that's what we're thinking about when we do that. Okay, so that's the thing we need to worry about. I'm going to scroll down to our diagram here, and I'm going to explain it to you so that it makes sense. So the first thing, I'm going to draw it at the same time again, because I think that's important. Okay, this right angled triangle represents our incline. Theta is the incline to the plane. So in this case, the road is banked at 15 degrees. Okay, that's the first thing. And then we represent our body, or whoops, that's not a very good rectangle. That's a very wonky rectangle. So would represent our car with a rectangle. Okay, that's usually what we do. That's about it. Now, in terms of how we draw or where we draw our forces from, I need to do a bit of talking about that. So normally the weight is, so before you copy at the moment, just listen to this bit. Normally we put the weight down from the center of mass, okay? The normal force is from the surface it interacts with, okay? So technically it should be, and it's at right angles from the surface like this, okay? For the purposes of this diagram, we're not doing it from the center of mass. It's a bit easier to do it from the center at the base of it because of where all the angles are and things like that, okay? But all the forces are coming from that, when I say idealized one spot. But if you ever see forces for the normal force coming from a surface, that's why. Technically, that's actually better. And if you see the weight coming from the center of mass, that's actually also technically better. But I just needed to show you this and tell you that. Alright, so from the center at the base of it, that's where we're going to start all our forces from. The first thing is our weight or force, we'll say it's Fg is equal to mg. You can put W, that's fine. I think your textbook uses Fg, that's why I've done that. Okay, now from there, we then can draw some other things. Now, what do I need to draw? Give me a moment. I need to refer to the textbook for a second. Okay. What else? The other thing we can definitely draw is the, let me just move over so my head's not in the way, the normal force. Now, the normal force is always at right angles to the surface that the object is on. Okay, so I'm going to draw that as best I can from the circle, not the circle, the point of the forces. It's supposed to be a straight line. So that's going to be at right angles, and that's your normal force. I'm going to make that F with a subscript N, just to make that really obvious. Okay? So those are the two forces that we definitely know about, and the other force that we know is happening to this car is the friction force. Now, the friction force is going to be happening on the wheels. So it's the surface of the road happening to the wheels. Okay, it's going to happen along the road, and that friction force is going down the plane because you're going in towards the turn. So we're going to draw it down the surface of the plane like this. Okay? So those are the three main forces we're going to concern ourselves with. And the other one that we care about, which is actually really important too, is our centripetal force. Now, where does the centripetal force go? The direction? Center of the motion, yeah? And we're going to assume that it's towards the left because it's banking that way. It's always parallel to the horizontal surface. So centripetal net force is always parallel to that horizontal surface. Okay? So those are your main, your starting forces. Now, let's look at our normal force. This is where we are going to do, in maths terms, it's called resolving the forces. We're using trigonometry to do that, okay? So we're resolving the forces into its vectors. So we're going to make another right angle triangle, okay? So, and I'm going to do it in dotted lines, like this. So we've made the right angle triangle there, okay? Now, the vertical is the y. We're going to denote it. Vertical is y, x is going to be the horizontal, and that's going to be Fn, and that's in the y direction, okay? And then in the x direction, we've got Fn, and it's in the x direction. We can use trigonometry to actually calculate that, because the normal is actually, we're going to calculate that later. But first of all, we need to understand which angle are we referring to. Now, I'm going to tell you right now that the angle here, which at the bottom of the blue triangle for the normal forces, is the same as the angle of the incline. The main thing you need to know is that angle down there is the same. So if we know that, go back to the blue triangle. With the blue triangle, okay, the x direction is opposite and the y direction is adjacent. So based on that, if you're using trigonometry, your Fnx will be Fn sine theta, and your Fny is your normal times cosine theta, and that's where it comes from. Now we'll look at the friction triangle, which is the red triangle, or burgundy, red, pink triangle. So I'm going to put the vertical down, and then across to the left is the friction. So in terms of the horizontal, it's F subscript Fx, and then the vertical is F subscript F and then Y, okay? Now, we already know the angle, so the opposite is the y direction and the adjacent is the x direction. So if we look at the vertical direction, it'll be Ff sine theta, and for the x direction, it'll be the friction, so the hypotenuse, Ff cosine theta. That's where all of it comes from. Which bit do you need me to repeat? The vertical, okay, is, we've made that FFY. The horizontal is the FFX, okay? Now, we know that theta is in that bottom left-hand corner, like, because that's the angle to that's the banked incline. Yeah, that's your original, that's 15 degrees. So if we label it based on trigonometry, your vertical is opposite and your horizontal is adjacent. So we go back to the vertical. Your vertical has to be your hypotenuse multiplied by the sine theta. And that'll be the y component. Yep. And then your x, your friction x will be the hypotenuse Ff times cosine theta. That's where it comes from. So that's where all of the diagrams come from, the labeling. Now I'm going to rub out my right-hand diagram and I'm going to move across because I want to get us towards doing the calculations. The left-hand diagram is what you need. It's the same. So ultimately, we are wanting to calculate the maximum speed at which this car can go around the bend without skidding off. And we're going to first do a vertical forces balance. Now, I've already pre-highlighted the vertical forces in or this lavender color, so it's really obvious to us. Now, there's no acceleration component in the vertical because we're not going up or down, if you think about it. We're staying in the same plane of motion vertically. We're not going up or down. Okay, so vertically the forces are balanced. So the F net in the y direction is equal to 0. So if you think about it, the up forces are going to equal the down forces. Another way of thinking about it is up plus down equals 0. That's the other way of thinking about it. I'm just going to put that in brackets. If you're wondering what the 0 means, they're all the same way of saying the same thing. Now, let's look at the up forces. The normal forces are what are pushing up against the car. So your up forces, but only the vertical component is your F and Y. So it's the Y component of your normal force. And then that's going to equal all of your down forces. So your down forces are your friction down force and the weight of the car. So that will be Fy, so the Y component of your friction force, plus your weight, which is mg. I'll write it as Fg, and then we'll substitute other stuff. Your variables, Fg. Okay? That's what we've got. Now let's keep going. F and Y is the same as your normal force times cosine theta, and that equals your F sine theta plus your mg. Okay? Now I'm going to go pretty quickly at this point. At the end of the day, we will be solving for Fn. That's the purpose of this part. Okay? At the moment, right now, from now on, we're going to be substituting numbers and rearranging. Let's substitute our numbers in. We have Fn cosine 15 degrees is equal to 15,500 times sine 15 degrees plus, I'm going to scroll to the right because I want more room. Our mass of our car is 1,300 kilograms times 9.8 meters per second. We'll keep going. So my normal force is equal to, so what you can do is you can actually put this all into the calculator at once. Your answer should be 17,342.6310. You need to save that answer in your calculator. The reason being is we're going to use that answer later in the horizontal forces balance that we're going to do next. So it's best not to round, even though we've kept a lot of significant figures. Don't round it yet, because we needed to use to calculate the next thing. So this is the size of the normal force. So this is how much the ground is pushing back onto the car at that right angle to the surface. Okay, so now we're going to look at the horizontal forces. With horizontal forces, what we're going to do is the net force is equal to, so F net, the centripetal force and it's equal to the sum of horizontal forces. So that's how that works. Our sum of horizontal forces is equal to F net. Now, I'm going to scroll up to our diagram so we can see it again. In terms of our horizontal forces, I've highlighted them in yellow, the ugliest yellow I've ever seen, but that's what I've got. It'll be the horizontal component of the normal force plus the horizontal component of the friction force are what we need. Okay, that's giving us our resultant centripetal force here. Okay, so let's go down so we can write that in. So our x component of the normal force add the x component of the friction force is going to equal the net force, net centripetal force. Let's substitute more information. So Fn times sine theta plus F friction times cosine theta is equal to, now the net force is also known as mv squared divided by r. So remember, centripetal force is mv squared divided by r. Now we can substitute the information we had before, and the normal force that we calculated before, which we have saved on our calculator, 17,342.6310 on your calculator, it will be longer, times sine 15 degrees, plus your friction of 15,500 times cosine 15 degrees is equal to your mass, which is 1,300, times your v squared, which we're going to solve for, divided by our radius, which is 13.0. Now, on our next line, your answer here should be 19,460 point, it'll be quite long, so 4535078, that's what I had on my calculator. That will equal, here, the 1300 divided by 13 is 100 times v squared. We'll keep going. So, v squared is going to equal this 19,000 number divided by 100. So then v squared is equal to 194.6045355078. Then you take the square root of this number. Our final velocity will be, the number is 13.95. There's quite a few decimals, but if we're doing it to 3 significant figures, it will round to 14.0 meters per second. And that's the maximum constant speed. So that's what's going to happen in terms of, that's the maximum constant speed that the car can go into the bend without skidding off. If the car goes any faster than this, it'll skid off the bend, as in you'll, so you probably have experience when you're driving, you go too fast into the corner and you shoot off, right? But if you're going at 14 meters per second or less, you'll be able to turn into the bend quite comfortably. So that's what they're talking about, is the maximum design speed or that maximum speed there.
This has been Education with Eleanor, and I hope you liked this video. If you did, hit the thumbs up, and remember, physics is a story, and subscribe. Bye!